Welcome to Maths with EJD. In this video, still on generating functions, we are looking at partial fraction decomposition with generating functions. And the idea is to learn how to simplify generating functions using partial fraction decomposition. And this will allow for easier expansion and identification of patterns. So the first question is, what is partial fraction decomposition? Interestingly, under the calculus playlist, um, there's an aspect where we talk about um, s- uh, integration by resolving into partial fractions. So I think I did an elaborate explanation on different types of decomposition there. So you can check that out. But for now, partial fraction decomposition is a method of breaking down complex rational function, complex rational function into simpler fractions, making it easier to manipulate or expand. This is crucial in generating functions where denominators might involve products of terms, as it allows term by term, as it allows for term by term analysis. Okay, so let's take an example. Decompose and expand the generating function g of x equals 1 over 1 minus x squared into 1 minus 2x. Okay, so this is a generating function. We need to decompose and expand that. Okay, so if you check what I did for partial fraction decomposition, you'll see that here we have two types. We have two kinds of expressions with two different approaches in that one problem. So we have g of x equals 1 over 1 minus x raised to power 2 and 1 minus 2x. So first of all, the two parts in brackets are actually they are linear terms. So for instance, this is linear, this is linear. But then because this one has power, then we say it is a repeated linear term. And there's a way to handle that when we are trying to resolve it in partial fractions. And this is exactly the way to go. We have so I say given this, we resolve into partial fractions as follows. Okay, so we have now 1 over 1 minus x squared into 1 minus 2x. And that will be similar to, okay, that will be similar to a over 1 minus x. Now, because this is a linear term, we say a 1 over a minus x plus, now because it is repeated, then we say b now all over 1 minus x raised to power 2. Still that. So if you have up to power 3, we have to keep going like that. Like if it was power 3, we have 1 a over 1 minus x plus b over 1 minus x squared plus c over 1 minus x cubed raised to power 3. Then now 1 minus 2x is just a linear term, so we just have that to be c over 1 minus 2x. So once we get this right, every other thing can go. So here we can multiply through by the LCM. So say multiply through by the LCM. I mean, obviously, the LCM here is 1 minus x squared into 1 minus 2x. So the left-hand side, you multiply that, so that will just remain 1. And then when you come here, 1 minus x cancels 1 minus x. So I'm just going to go straight and write out what that should be. So on the right-hand side, we have 1 because 1 minus x squared times 1 minus 2x cancels all of that. And for a, right? So we have a over 1 minus x goes out. So we have just 1 minus x, 1 left, and then 1 minus 2x left, like that. So because 1 minus x cancels one of this, and we have just one of that left. Then when we go to the b, so 1 minus x squared cancels 1 minus x squared. So we have 1 minus 2x remaining. So that will be b into 1 minus 2x. Then for c now, 1 minus 2x cancels 1 minus 2x. So we have c into 1 minus x all squared. Then we can use what is called the cover-up method for easy solution of all these terms. The other part is you can extract, you can expand everything and then collect like terms and all that. But I think that's going to waste time. So we can just use the cover-up method. Uh, we now use the cover-up method, to obtain the values of A, B, and C. Okay. And the way to do that is this. Look at all the terms. This is 1 minus x. All right. So you know that if you set 1 minus x to 0, imagine that if you set 1 minus x equals 0, that implies that x is equal to 1. That means if you set x to be equal to 1, you're going to cancel out some terms so you can get another term. All right. So let's do that now. So we just say set x to be equal to 1. So if you set x equals 1, so the left-hand side remains 1 here. You have 1 equals, on the right-hand side now, you have a into 1 minus 1. All right. So you can already see 0 coming out of that. So you have 1 into 2 into 1. You have that. Then plus b into 1 minus 2 times 1, because x is 1 now, plus c into 1 minus 1 all squared. So if you tidy that up, so this is a equals 1 equals a into 0 into 1 minus 2, that's minus 1, plus b into minus 1 plus c into 0 squared. So you can see already that this is 0 and this is also 0. So we just have 1 equals minus b. Easy. So that implies that b is equal to minus 1. So we have the value of b settled. Okay. So b is known to be minus 1. So that is done. So another thing we can do is this. We have set 1 minus x to 0. And what else can you set to 0? That's the idea of the cover-up method. You want to set terms to 0, one after the other, so you can eliminate possibilities. So here you have 1 minus 2x. That's the other term you have there. So you see that if you have 1 minus 2x equals 0, that implies that you have 1 equals 2x, which means that 1 over 2 is equal to x. So if you can set x to be 1 over 2, then you can also eliminate some terms. So let's do that. Okay, so we can say let x be equal to minus 1. I mean, let x be equal to 1 over 2. So if that happens, you go back to the original expression. So you have 1 into a, 1 equals a into 1 minus half. Okay, that's 1 minus half here. Then you have 1 into 2 multiplied by half. Okay, then you have b into 1 minus 2 times half plus c into 1 minus half squared. Okay, so that is 1 minus half all squared. I think that's what that is. That's 1 minus x squared. Okay, so let's tidy things up. So you have 1 equals a into minus half here into 2 times half is 1. 1 minus 1 is 0 plus b into 1 minus, okay, we can tidy that up straight. 2 times half is also 1. 1 minus 1 is also 0 plus c into minus half all squared. So this just cancels out because of the zeros. So you have 1 equals minus half raised to power 2 is 1 over 4c. So that is c over 4. Okay. So if you cross multiply, so c is simply 4. Does that work? 1 minus half, right? Yeah, that's it. 1 minus half. Yeah, I'm sure that is correct. So that's 1 minus half. So 1 minus half. Okay. 1 minus half. Okay, even this is plus and this is also plus. So, but that doesn't still change the fact that it is 1 over 4. So it's positive, right? So it's 1 over 2. Yep. Okay, so that works. So C is equal to 4. So we have our C sorted now. Now, if you go back to the original expression, that's this expression right here, you discover that there's nothing you can set to 0 again. So now you can pick any random value, but make it as small as possible. So since you already have 2 of the values, any value you pick will eliminate all the x's, then you can substitute the 2 values you have. So, but I see that what can work here is to, so we can pick 0. So you can just say, let x be equal to 0. So if x is equal to 0, the right-hand side is 1, and the left-hand side, you have 1 minus x. So that would just be a into 1 minus 0 into the next one is 1 minus 2x. So that is 1 minus 2 into 0, then plus b into, so b, you have b into 1 minus 2x again. That is 1 minus 2 times 0 plus c into 1 minus x squared. That is 1 minus 0 squared. Okay, think that works. Yeah, that's it. So let's go ahead. Now here, you may not have something eliminating, something canceling out outrightly, but at least it simplifies it so you can now go on. So 1 minus 0 is 1. Then 1 minus 0 again. 2 times 0 is 0. 1 minus 0 is also 1. Plus b into 1 minus 0, another one. Plus c into 1 minus 0 squared. 1 minus 0 is 1 squared. That's 1 again. So you see that 1 is equal to a plus b plus c. Now, the lovely thing is that we already know b and c, I believe. We have b to be minus 1, and c is 4. Okay, so we have 1 is equal to a plus b is 4. I mean, what is b? I think b is minus 1. B is minus 1, and C is 4. So minus 1 plus 4. So we have 1 equals A minus 1 plus 4. So 1 equals minus 1 plus 4 is plus 3. So that A now, so 1 minus 3 is equal to 1 minus 3 is equal to A, so that A itself is minus 2. So A is minus 2. So we can conclude that therefore A is equal to minus 2. B is equal to A is minus 2. B is minus 1. A is minus 2. B is minus 1. And C is equal to 4. C is equal to 4. Okay, so with all of that now, then we can go back to the original expression. Remember the original thing, so we can say therefore 1 all over 1 minus x squared into 1 minus 2x, which is similar to a over 1 minus x plus b over 1 minus x squared plus c over 1 minus 2x can then be equal to a now is minus 2. So we have minus 2 over 1 minus x plus b, which is 1 minus x squared plus, oh, yeah, b now is minus 1. B is minus 1. So that would be minus 1 all over 1 minus x squared plus c. C is 4 all over 1 minus 2x. So that's basically what we have for that. And with this now, we can break all these things down as much as possible, right? So that means that we can now expand each term, right? Using what we have, we can say, therefore, gx, I mean, what was the original thing we're given? G of x, g of x is equal to, so if you like, you can do 4 over 1 minus 2x, then minus 2 all over 1 minus x minus 1 all over 1 minus x all squared. So we can break these things down term by term. And then, so for instance, we know that, okay, this is g of x now. G of x is 4 into 4, 4 into 1 over 1 minus 2x minus 2 into 1 over 1 minus x, then minus 1 all over 1 minus x all squared. So we can rewrite that as 4 into 1 minus 2x raised by minus 1 minus 2 into 1 minus x raised by minus 1 minus 1 minus x raised by minus 2. So we can do all of those expansions one after the other. So let's try. This is really a long one. So we have 1 minus 2x raised by minus 1. So I'll just go fast and get the terms using binomial expansion. So we have 1 raised by minus 1, the minus 2x raised by 0 over 0 factorial. I'll just get first 3 terms to see the pattern plus 1. So minus 1 comes down now. So you have minus 1 into 1 raised by minus 2 minus 2x raised by 1 all over 1 factorial plus minus 1 into minus 2, 1 raised by minus 3, minus 2x raised by 2, all over 2 factorial, and all the terms go on like that. So, of course, the whole of this will be 1. We've done that a lot of times, so we know it's 1. So, and coming here, we have minus 2x, and this is minus 1. So, this is just plus 2x, right? That's plus 2x. And then, yeah, that works. So, 2 factorial cancels this 2. So, we have minus minus is plus, then this is of course 1. So that's plus 4x squared. So we have a kind of, so this now is more like summation from n equals 0 to infinity, from n equals 0 to infinity of 2 raised power n, x raised power n. For instance, when n is 0, you have 2 raised power 0, x raised power 0, that is 1. When n is 1, you have 2 raised power 1, x raised power 1. When n is 2, you have this is why we are doing this now. This is the same thing as this is more like 2 raised by 0, x raised by 0 plus 2 raised by 2 raised power 1, x raised power 1 plus 2 raised power 2, x raised power 2, you know, and so on and so forth. And that is why we have this summation right here. I guess I need to clean that up to make to really drive home that point. So we have a general pattern from what we have there already. So this is plus all the rest. So this is more like 2 raised power 0, x raised power 0, plus 2 raised power 1, x raised power 1, plus 2 raised power 2, x raised power 2, and so on and so forth. So it means that 1 minus 2x raised power minus 1 is the same thing as summation from n equals 0 to infinity of 2 raised power n, x raised power n. And this is really important. We've got this part. Then we go for the next one. We have 1 minus x raised power minus 1. So we do also that also. 1 minus x raised power minus 1. So we quickly treat that. This is 1 raised power minus 1 minus x raised power 0 all over 0 factorial plus minus 1, 1 raised power minus 2 minus x raised power 1 all over 1 factorial plus minus 1 minus 2, 1 raised power minus 3 minus x raised power 2 all over 2 factorial, and all of that continues. So this is the same thing as, of course, everything, 1 raised power minus 1 is 1, minus x raised power 0 is 1, 0 factorial is also 1. So everything there goes to 1. So here you have minus x and 1. So this is just x. Then when you come here, 2 cancels 2 for sure. So minus x squared is x squared. Then everything is positive, right? So we have plus x squared and all that. So that means that this is more like, so for this now, we simply have, this is x raised power 0 plus x raised power 1 plus x raised power 2, and so on and so forth. So it simply means that 1 minus x raised power minus 1 is equal to summation from n equals 0 to infinity of x raised power n. So that's that part now. So it's coming out good. Then we have the next one, which is 1 minus x raised power minus 2. Let's see the pattern for that. 1 minus x raised power minus 2. Okay, so for 1 minus x raised power minus 2, we have this 1 minus x raised power minus 2. Again, that's 1 raised power minus 2 minus x raised power 0 over 0 factorial plus minus 2 into 1 raised power minus 3. This is minus, yeah, minus 2, 1 raised power minus 3 minus x raised power 1 all over 1 factorial plus the next minus 2 minus 3, 1 raised power minus 4 minus x raised power 2 all over 2 factorial and all of that. So we have, of course, 1 raised to minus 2 is 1, minus x raised to 0 is 1, 0 factorial is also 1. So everything there is 1. So here we have minus 2 minus x, that's plus 2x. Then next, 2 factorial cancels just 2. Then everything is still positive because minus x squared is x squared. Then we have, that's plus 3x squared, and that goes. So what's the general pattern here? If you can check, that's more like this is n x, and can we say that? That's like nx raised power. Okay, it doesn't start from 1. It doesn't start from 0 now. So it doesn't start from 0. So here we see nx raised power 1, or better still, this is like 1x raised to power 1 plus 2x raised to power 2. Like it's not working. Okay, I think this is it. 1x raised to power 0 plus 2x raised to power 1. Yeah, I get the pattern now. Plus 3x raised to power 2, and so on and so forth. So that's more like n, if the n, that's nx raised to power n minus 1. Okay, that's more. So from that pattern now, we can see that that is actually summation. Okay, well, let me, just like the others, I have 1 minus x raised to power minus 2. And that is summation from n equals 1, not 0 now, n equals 1 to infinity of nx raised to power n minus 1. So we have all the three patterns. So we can bring them back into the original expression This is a lengthy one, but thankfully we are coming to the end of it. So we can say now that therefore g of x, which is equal to the last place where we stopped. So we can say therefore g of x, which is equal to um 4 into 1 minus 2x raised by minus 1 minus the next one, uh minus 2 into 1 minus x raised by minus 1. So minus 2 into 1 minus x raised by minus 1 minus 1 minus x raised by minus 2. I think that's all we have. I think so. Yeah. 1 minus x raised by minus 2. Yeah. I think that's about it. So now we can fix those values. So g of x now is equal to 4, 1 minus x raised 1 minus 2x raised by minus 1 is 2n xn. Okay. So that's summation from n equals 0 to infinity of 2 raised by n, x raised by n, minus 2. Then 1 minus x raised by minus 1 is summation, that's xn in short. So summation from n equals 0 to infinity of xn. Then the last one, minus 1 minus x raised by minus 2, which is the last one we got, will now be minus summation from n equals 1, mind you, to infinity of nx raised by n minus 1. So now we have what we need. So we have split it apart using partial fraction, and we have now expanded it. So you can see that the final series is the sum of these expansions. So by simplifying each part, we can now isolate the coefficients of each power of x and use them to solve combinatorial or algebraic problems. All right, so that's been a long one. I'd like to stop there. So be sure to subscribe to the channel and hit the notification bell so you can get alerted each time a new video is released. Comment, let me know how helpful these videos are. And let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Like and share so that more people can have access to this. Bye. See you in the next one. Don't miss it. Bye.